So I'll tell a little bit about brain-machine interfaces and how they're used for rehabilitation. The goal or the rationale of the brain-machine interface is to use brain activity to control machines, sensors, actuators, etc. So in a healthy person, if I want to move my arm, I actually don't think about it consciously, but I think about moving my arm, and there's a command from the brain to a series of structures, and then my arm moves. And when there is a lesion, this is not possible because the communication has been stopped. Many techniques have allowed us to study neural activity for many years now. And as time goes by, what happens is that we are able to decode what the brain is trying to do to some extent. So we look at some cells and we see that they fire a lot, they have action potentials, they have a lot of activity related to a specific activity. So for example, if we know exactly what the brain is doing, we can try to predict what the brain will do and what the body will do even before they do it. So in a healthy person, typically, we have an order from the brain to the arm, but as there's a lesion, this path is interrupted. And what the brain-machine interface does is that it bypasses the lesion and sends it to a machine. So at which everyone has been hearing about this for a while now, but where do we stand? What do we know? What do we not know? So the first experiments, they showed the ability of a monkey to control a robotic arm in 2 and 3 dimensions. More recently, a robotic arm was controlled by a human in approximately, I believe, 16 different degrees of freedom, which means 16 different movements combined. And now people are already using these for multitasking. So for example, having a third arm so that you can keep on writing while you're drinking.